Hello there and welcome back. So we're going to take a look at some more examples of how we can use spherical coordinate systems and triple integrals to calculate volume. So here we have the upper half of a sphere, and we want to find the volume of the sphere, but there is a little bit more. We have this 16z that we are multiplying this volume by. The dV, of course, stands for volume. So here we're taking our volume, multiplying it by something else. Now, if we imagine this as more of like a physics problem, this something else could be the density of the object. And the density of the object depends on the height of our sphere. So at 0, the density would be like 0, and as we go up, the density, of course, increases. So this would give us then the mass of our upper half of the sphere right here. Now we are going to have to convert to 16z right here. So let's go ahead and just set up our volume. Now they tell us E is the upper half of the sphere. This little E down here, they use different letters, D, R, E, all sorts of variables that they'll use right here. So all that really matters is if you see a letter down here, they're really, if you see a little bit of a letter down here, they're looking at the limits or the domains of our sphere. So let's go ahead and talk about this. So this is saying we are going to be integrating about a sphere. So let's go ahead and talk about our sphere then. Well, if here's my sphere, if from the pole, from the center, I draw my radial arm out until it hits the sphere, I know that the change in R, or rho, if here's at some point x, y, z, where I hit the sphere, I know that the change in rho starts at 0 and goes up to 4. Remember, that's just my change in radius. From the positive z-axis until I move down here, remember, this is our change in phi. Well, remember, at the top, phi is 0. Now, we only want a half of a sphere. So we're going to start up here at phi equals 0, and we'll end up down here, going all the way down here to the xy plane, where phi, of course, is pi over 2. Remember, all the way down is pi. So we go to pi over 2. And that is the ugliest looking phi ever, so I'm going to fix that. That looks a lot better. So we have our change in phi, we have our change in rho, and the last thing we need is theta. Well, coming from the xy plane, theta, remember, goes around. So theta is going to go from 0, and we go all the way around 2 pi. So that gives us E, our limits. And we can write them down here again. We know that the change in rho is 0 to 4. Our change in phi is 0 to pi over 2, and we just said the change in theta is 0 to 2 pi. So let's go ahead and set up our integral. Right, quick. Now I'm going to do something else a little bit different. Remember, it's E. It's just E, 16z dv. So we're going to change all of these. This we're going to convert. We have to convert this. And here's, of course, our volume, which, when we start setting this up, spread out the wealth, right? Let's write 16v. Well, 16z, I mean. Z, from up here, from way above here, we know z is just written as rho cosine phi. So I can just write this as 16 rho cosine phi. But remember, dv, in our new one, remember dv here is going to be rho squared sine phi. So, and then this, of course, has our variables here. So we can go rho squared sine phi, and then we have our d rho, d phi, d theta. Remember this part right here. This is our volume. That's our dV. That's our change in volume right here. And then we can just plug in all of our limits here. And, of course, d rho is first, so 0 to 4. d phi goes from 0 to pi over 2, and then d theta goes from 0 to 2 pi, my favorite mathematical wrapper. And then you would just solve that. Alright, so let's take a look at the next one. Ready? Hope you enjoyed that one. Let's take a look at our next one here. For number 2, we are asked to evaluate this integral where E is the region between the two spheres. Our first sphere has a radius of 1, our second has a radius of 2. And Z is greater than 0. So this is telling us we only want the top half of the sphere. Right here. So we don't want that top half. So when we graph this, now I'm only going to look at the first octant here, just to kind of, but you'll get the idea here. Now my first sphere has a radius, has a radius of 1. 1 goes like this, up 1. My second sphere has a radius of 2, goes out here, and 2, and 2. Now remember, we only want the part in the middle. So we're going to shade like this little middle part right here. So you kind of think of it like if this is like the center of the earth, this is like the mantle, then you have, of course, the crust. So we're looking at like the mantle of the earth, right? So we can kind of think of this as like the mantle. We're going to try to find the volume of the mantle of the earth here. All right, so let's go ahead and get our domains, or our limits here. Remember, for our limits, we need change in rho, we need change in phi, we need change in theta. Well, change in theta is easy. We are talking about the top half. Now remember, I only do the first quarter, so theta is going to go from 0 to 2 pi. Now, phi, remember, I'm starting here at phi, which is 0, and I'm ending here at phi, which is pi over 2. I only want the top half. If I want the full one, I would go from 0 to pi. So this one only goes from 0 to pi halves. And then rho, well, rho is just my radii. That's my radii. I'm starting at 1, going out to 2. So it's just 1 to 2. Now we do have this 3x minus 2y. We do have to convert this. So 3, well, what is x equal to? X would, remember, rho sine, excuse me, phi cosine theta minus 2 rho sine phi sine theta. And now when I find my volume, I'm just going to plug it all in. It's a long one, so I'm going to give myself some space. We're going to get in the inside 3 rho sine phi cosine theta minus 2 rho sine phi sine theta. Here we go. This is the next part. Here's our change in v, right? dv. Rho squared sine phi d rho d phi d theta. I'll put this in parentheses here just so it's like multiplying. And I change it. Now d rho is 1 to 2. D phi is 0 to pi over 2. And theta goes from 0 to 2 pi. And that would get our volume right there. Quick and easy to do. Alright, so for the last one, number 3, sorry, not the last one here, for number 3, let's take a look. Now we want to set up, but do not evaluate. My favorite phrase in mathematics. Do not seek the treasure. Okay, do not solve. So we want to find the volume of the common interior of this cone and this sphere. Now the sphere I can rewrite as just rho equals 4. That might make it a little bit easier. And so let's see if we can draw this out. Let's see if we can draw this. Okay. So we have a sphere of radius 4. And of course it's going to look like this kind of. If I just look at the first octant here. My cone, starting at the base, opens up. So we kind of see, whoops, hello, where they meet here. And then we're going to rotate that, right? So we're looking for this volume here. Now you got to remember, where they intersect right here, remember my sphere is going around, right? So it's going to have this little round part right here. So you can almost kind of imagine it looking like kind of like a little bit of an ice cream cone as we go all the way around. So obviously we do have to find out where the sphere and the cone meet. So let's go ahead and do that, where the sphere and the cone meet. The cone, I could write this as z squared equals x squared plus y squared. I can use that and plug that in here. So where I have x squared plus y squared plus z squared equals 4, I can now say this as z squared plus z squared equals 4, or z squared equals 2. And if z squared equals 2, we know that z equals z squared root of 2. So we found out where they meet in terms of. Alright, so I want to convert this to spherical. So I know that z equals rho cosine of phi. So I can say that root 2 equals rho. Well, what is rho here? So rho here is going to be, I did correct the mistake. Now this was really rho squared equals 4, so rho is going to be 2 here. So what is that telling me? That if I start from the bottom here, if I go out, remember I only want this area part in between here. If I go all the way out, this is going to be my maximum rho, which is going to be 2. So my rho is always, the minimum is 0, always going to go up to 2. So z, which is equal to rho cosine phi, is going to give us root 2 equals 2 cosine phi. And I can solve for cosine by taking the inverse cosine of cosine root 2 over 2, and that's phi, which is going to give us pi over 4. All right. So now we basically have all of the limits here. So let's take a look at the limits for this one. I need the change in rho, the change in phi, and the change in theta. So the change in rho is going to go from the bottom all the way up to this little piece up in here, which is going to be 2. So it's going to go from 0 to 2. Phi, I'm starting at the top here, and phi is just going to be this angle right here, which starts at 0 and ends where they intersect. Phi, which we just said was pi over 4. So 0 to pi over 4. Theta, we want the entire bit, so we can go all the way around. So theta is going to go from 0 all the way to 2 pi. And now we can write our volume, our triple integral, space these out. Remember, this is going to be rho squared sine phi d rho d phi d theta. Remember, this is our change in rho, that's our dv. Now we look at our bases, which goes from 0 to 2, change in rho, change in phi, 0 to pi over 4, and then 0 to 2 pi. It looks ugly, but they're not terribly bad to solve. Alright, so there's our answer right there. Hope you guys enjoyed the video. Go back to video number 3. We'll take a look at a couple more examples. Bye-bye. See you then.